Okay, well, I hope you had fun watching this video, and now let's keep going. So, air pressure comes from the fact that we have the atmosphere above us. And the atmosphere is something like 20 kilometers thick. Now, this number, 20 kilometers, is a very fuzzy number because what happens is that the atmosphere is very thick and dense down at the bottom, and it gradually becomes less and less dense. And there's no transition between being in the atmosphere and being in space. What happens is the air just becomes less dense, less dense, less dense, less dense. But even when you're 1,000 kilometers, 100,000 kilometers up, there's still a little tiny bit of atmosphere left. And as a matter of fact, satellites, the space station, and so on, as they orbit, the leading edge of those spacecraft are constantly running into air molecules from the atmosphere. And the satellites, the International Space Station that are low, that are close to the atmosphere, they're feeling a little bit of friction all the time. And the International Space Station, for example, has to turn on some rockets once in a while to get it to speed up again. Otherwise, it would just deorbit. It would fall back down. Okay, I got sidetracked. But anyhow, so let's talk about 1 square meter. Right. So I've got a square meter right here, and let's make an imaginary rectangle, tall volume here, and that goes all the way up to the top of the atmosphere, wherever that is. It's kind of fuzzy. Well, anyhow, if you were to do that, the weight of all of this air would be 101,325 newtons. And that's a lot of newtons. That's equivalent to about 11,000 kilograms. Another way of looking at it is that there's 11 metric tons of air above that square meter. So it's, a square meter is 1 meter by 1 meter, so it's like the top of your desk, and there's that much air above it. It's a tremendous amount. Now you would think, okay, so that would just crush the desk, but fortunately there's air underneath that's pushing up and so on, so we don't actually feel all of that air. Now, and then you saw the can getting crushed, and so that can got crushed because they've created an imbalance. The air inside the can was gone, and so there was air outside pushing in and nothing on the inside pushing back out. And so once you lose that balance, then crazy things happen. I have here a tire pressure gauge, and this thing's remarkably sophisticated. It must have a little computer inside. Right now, it's reading in pounds per square inch. It says 0.0 psi. If I press this button, it's now saying 0.00 bars. And if I press it again, it's now saying 0 kilopascals. So this thing is pretty cool. I use it all the time to check the pressure on my car tires. Now, this pressure gauge reads gauge pressure. And the difference between gauge pressure and real pressure, true pressure, which we call absolute pressure, is that what this is really doing is it's telling us the difference between the pressure in the tire and 1 atmosphere. So it's basically telling you the difference between the pressure inside and outside of the tire. So let's say my car had a flat tire. The pressure gauge would report 0. But actually, there's still some air, a little bit of air inside there, and that air is going to be at the same pressure as our environment, right? So and the pressure in our environment is 101 kilopascals. Now, if I have a tire that is properly inflated, then this gauge would read 30 psi, or 202 kilopascals. Now look at my notation here for this physics class and so on. I'm going to be saying P with a little g, which means gauge. So that'll mean gauge pressure. If it's just P, that's going to mean absolute pressure. And the difference between a gauge pressure and absolute pressure is the pressure of the atmosphere, which is 101 kilopascals. So you see here, the absolute pressure is 303 kilopascals, because 303 is 202 plus 101. Plus 101 gives us 303 kilopascals. And yeah, so gauge pressure is the absolute pressure minus 1 atmosphere. Let's look at pressure in a different scenario. When you go diving underwater, you've probably had the experience when you went diving at a swimming pool in the deep part, that as you go down deep, you feel water pressure against your ears. So that's caused by the weight of the water above you. Let's take a look at that. So the weight of the water that's above you is going to be the mass of the water that's above you times g, right? Weight is mass times gravity. And so that's going to be the mass is going to be the density of the water times the volume of water that's above you. And then that's volume is going to be the area. So we need to kind of make an assumption, what's the area of your body, kind of model you as like a flat piece of cardboard or something with a certain area. And so the volume of the water above you is the volume of this water here, right? And so it's going to be A times H, and now you're going to get the weight of the water, you're going to multiply by rho and G. Okay, so that's how you would figure out the weight of the water above you. Now let's think about the pressure. Pressure is defined as force divided by area, and so we have the weight of the water that's above us, rho AHG over the area. And looks like we have some canceling going on between the areas. And so the pressure that you experience when you're down underwater is the density of the water times G, 9.8, times how deep you are, H. H is the height of the water above you, or it's how deep you are. Now, this pressure here is going to give you the gauge pressure, right? It only includes the force of the water above you. It's ignoring the force of the air that's above that. So if you want to take that into account, if you want to get the absolute pressure, then you're going to add 1 atmosphere to it. And so the gauge pressure, the absolute pressure is going to be the gauge pressure, rho GH, plus 1 atmosphere. Okay. Let's see. Yeah, I have in parentheses that they write P sub AT, where AT must stand for atmosphere. Okay, so let's take a look at a little example. What would be the pressure, the absolute pressure, 3 meters down or 10 feet down, right? So most good big, university type swimming pools go down 10 feet. So let's say you went 10 feet down underwater. So you've got the pressure is rho GH plus the atmosphere. So rho is 1,000 kilograms per cubic meter. G is 9.8. Your depth is 3 meters. We are going to add to that 101,000 pascals. Now we got to watch out a little bit for the units here. Now kilograms times newtons per kilogram, right? Kilograms are going to cancel. And the meters are going to partially cancel the meter squared. And so the units of this stuff here is newtons per meter squared. Oh, but that's okay, because you see a Pascal is supposed to be a Newton per meter squared. So we're okay. You see, we're doing pascals and pascals. You need to have the units match. Okay, anyhow, doing the arithmetic, multiplying and adding, you get 29,400 pascals for the water pressure above you, and then you have the atmosphere here. You add it up and you get 130,400 pascals. Okay, so next we're going to be looking at some situations that involve balancing pressures. An example of that would be a tube here that has been filled with liquid, and intuitively you know that if you fill up a U-tube like this, it's going to fill and settle to where the water level or fluid level on both sides is equal. This is actually used by building contractors. They can set up a long hose if they're seeking to figure out whether they've got things level, like they're trying to get the foundation of a house perfectly horizontal. They can fill this up with water, and as they fill it up with water, it fills up with water. And if it just barely gets to the top here and to the top here, they know that this line would be perfectly horizontal. Now, the reason that this works is because when the level here equals the level here, then the pressure here equals the pressure here. The pressure here equals the pressure here, and so on. And so going left and right, if you have equal pressures, then the water will not flow to the left. The water won't flow to the right because you have equal pressures. You have equilibrium. And that's the approach we're going to be taking for the problems. But before we go and use pressure equilibrium to solve problems, I want to bring up an alternative way to do this type of problem. And that is to keep in mind that systems, like, this is a sort of system, will always seek the lowest potential energy. So, here's a system that you're super familiar with by now. If I have a pendulum, it's going to be bouncing back and forth, and eventually it'll slow down because of friction, and the potential energy gradually gets turned into heat until finally there's no more potential energy left, and this is where it settles down. So this is an example of a system that seeks its lowest potential energy. Another example would be a bowling ball on a hill or something. It's going to go back and forth, and there's friction slows it down until finally it ends up at the bottom, at the lowest potential energy place. If you think about it, springs do the same thing. And this suggests an alternative way to find the equilibrium position of systems, but it involves a little bit of calculus. You see, what you could do is, if you can figure out a way to write the potential energy as a function of x, and then take the derivative of that, du dx, then you, when this is equal to 0, you've either found a minimum or possibly you found a maximum. So this is not what you want. You want to find this. And this would get you an equilibrium position. And oftentimes, this is easier than working out the forces. All right, let's take a look at Mercury barometers. I'm going to add to the playlist this video here. If you go into YouTube and you search Mercury Barometer, this video will come up. It's pretty good. And so now let's talk about what she's going to show you here. Mercury is this very dense liquid, and this Hg, by the way, is the chemistry symbol for mercury. And what I've got here is an upside down tube. The way I've got it drawn, it looks like a test tube, but it's got to be a lot longer. It's got to be almost a meter long. So it's going way up. And at the top, there's no air. It's a vacuum. The pressure is 0. And then here you've got this liquid. And you would think that the liquid would just go whoosh, flowing out. However, it doesn't, because the end of the tube is in more mercury. And at the same time, the Earth's atmosphere is pushing down. So we have air pressure or atmospheric pressure pushing down here. That air pressure works its way up. And so what happens is you reach a balance between the mercury pressing down and the air pressure pressing up. When you first make a mercury barometer, of course, it's going to go bounce, 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 but it'll quickly, there's enough friction that it'll quickly settle down, and it will get to a particular height h from the surface of this mercury puddle to up here. And the question is, how high is h going to be? Now, the answer to that question will change depending on the weather. As I already mentioned, in bad weather, the air pressure is low, and so this thing, so the mercury will work its way down a little bit because there's not as much air pressure. And in good weather, the mercury level will be a little higher. But anyway, let's figure out what H is for one atmosphere, for a regular day, so to speak. So you have a balance between atmospheric pressure here and the downward pressure of the mercury, which is the density of mercury times G, which is 9.81, times the height, which is what we're looking for. So you have the height equals the atmospheric pressure divided by rho G. And I'm plugging in the numbers. Atmospheric pressure is 101,325 pascals, also known as newtons per square meter. Here is the density of mercury, 13,590 kilograms per cubic meter. By the way, this is 13 times more dense than water. Water is 1,000 kilograms per cubic meter. So mercury is really dense. Okay, and then here is gravity. Now, I decided to use newtons per kilogram because you see it cancels newtons here. The kilograms cancel, and the meters squared are partially canceled out by meters cubed here, and so you're left over, meters left over. So the height is 0.760 meters. Now, when I was a kid, the TV news weather report would always tell us the air pressure in millimeters. They don't seem to do that anymore because there's all the fancy radar stuff. But when I was a kid, the radars didn't exist, and when they told us the pressure, that was useful information for figuring out what kind of weather we would expect the next day. Yeah. Now, you still see this term used, 760 millimeters of mercury. If you hear that phrase, what they mean is 1 atmosphere of pressure. Okay. Now, I have a question for you. What would the height be if you used water instead of mercury? So try to figure it out. And the answer was in the previous slide. Next, I'd like to show you how one of the examples in the textbooks gets started. So I'm looking at example 15-4. In this example, you've got YouTube, and it's filled mostly with water, but there's just a 5 centimeters here of the tube that is filled with oil. So it's water, it's oil. And the level of the water is up to here, whereas the level of the oil is here. And there's the interface between the oil, which is floating on top of the water, is here. And so the first step in doing the example, where the physics is in figuring out what is the height difference between the level of the water here on the left side and the level of the water here on the right side. Now, intuitively, you know that this is going to be a little lower because the oil is pushing down on the water. Now, that's okay, but in order to actually figure out what this height difference is, you need to use the idea that the pressure difference at the bottom has to be 0. In other words, the pressure pushing to the left has to equal the pressure pushing to the right. And that's basically saying it's not the water, the fluid is not going to accelerate to the left or accelerate to the right. We have equilibrium. For that to be true, the pressure here has to equal the pressure here, and going all the way up, until finally you come to the conclusion, oh, the pressure here, which I'm calling pressure B, the pressure here, has to equal the pressure here. And I'm calling that pressure A. So that's our equilibrium condition. Here it is. Pressure A has to equal pressure B. That's enough for us to get the answer. So let's figure out what pressure A is going to be. And we can figure that out because you have this much water pushing down, right? So it's that much. And so the pressure right here is going to be the density of water times gravity times the height. And then the pressure here is going to be the density of oil times gravity times the height of the oil. And we solve for the height of the water. And what we did is we divided both sides by the density of the water. The gravity has canceled out. We plug in the numbers, 5 centimeters. And then we had the density of the oil was 920. That was a given right over here. The density of water is 1,000 kilograms per meter cubed. You should remember that. And so it comes out to be 4.6 centimeters. Now, I know that usually I tell you, if you see centimeters, you want to convert to meters. But this is a case where we didn't have any accelerations or any complicated physics, so it turned out to be okay to just stay in centimeters. But you know, if you are worried about it, you can just go ahead, convert to meters, and then if the problem happens to want the answer in centimeters, you could just go and convert back. Next, I'd like to show you how one of the examples in the textbooks gets started. So I'm looking at example 15-4. In this example, you've got YouTube, and it's filled mostly with water, but there's just a 5 centimeters here of the tube that is filled with oil. So it's water, it's oil. And the level of the water is up to here, whereas the level of the oil is here. And there's the interface between the oil, which is floating on top of the water, is here. And so the first step in doing the example, where the physics is in figuring out what is the height difference between the level of the water here on the left side and the level of the water here on the right side. Now, intuitively, you know that this is going to be a little lower because the oil is pushing down on the water. Now, that's okay, but in order to actually figure out what this height difference is, you need to use the idea that the pressure difference at the bottom has to be zero. In other words, the pressure pushing to the left has to equal the pressure pushing to the right. And that's basically saying it's not the water, the fluid is not going to accelerate to the left or accelerate to the right. We have equilibrium. For that to be true, the pressure here has to equal the pressure here, and going all the way up, until finally you come to the conclusion, oh, the pressure here, which I'm calling pressure B, the pressure here, has to equal the pressure here. And I'm calling that pressure A. So that's our equilibrium condition. Here it is. Pressure A has to equal pressure B. That's enough for us to get the answer. So let's figure out what pressure A is going to be. And we can figure that out because you have this much water pushing down, right? So it's that much. And so the pressure right here is going to be the density of water times gravity times the height. And then the pressure here is going to be the density of oil times gravity times the height of the oil. And we solve for the height of the water. And what we did is we divided both sides by the density of the water. The gravity has canceled out. We plug in the numbers, 5 centimeters. And then we had the density of the oil was 920. That was a given right over here. The density of water is 1,000 kilograms per meter cubed. You should remember that. So it comes out to be 4.6 centimeters. Now, I know that usually I tell you, if you see centimeters, you want to convert to meters. But this is a case where we didn't have any accelerations or any complicated physics, so it turned out to be okay to just stay in centimeters. But if you are worried about it, you can just go ahead, convert to meters, and then if the problem happens to want the answer in centimeters, you could just go and convert back. Now there's one more small point that I want to add before leaving this problem. These pressures here, I did not include atmospheric pressure. So technically, I guess these are gauge pressures. This is a gauge pressure. But since we have the atmosphere, the P atmosphere here, and P atmosphere here, it's going to add to both sides, right? You're going to have plus P atmosphere and plus P atmosphere. And so these are going to cancel out and cancel out. Now, the book did a slightly better job than me. They did not forget this, and they go through and they show this to you. Okay, so now what I'm going to do is I'm going to go back to this little bit of the notes and talk about that for just a second. Okay, so I would want to mention something called Pascal's principle, and I suggest that you look at the book and read page 508. This is something that hydraulics uses all the time, and hydraulics is like super useful. A lot of our elevators are pushed up by a hydraulic piston, and garbage trucks have hydraulic pistons, and cranes and backhoes and bulldozers, all of that stuff. So hydraulics work on the Pascal's principle, and what the principle says is that if you have a source of pressure, so in the case of a truck or something, you have a pump, and there's a little reservoir of oil, like a little bucket of oil, and the pump is pumping the oil into this pipe, and the pump achieves very high pressure, hundreds of atmospheres, but the pump doesn't have to be a big honking machine. It can be really small, and all it does is it just squirts a little bit of oil into the pipe per second. And so it just keeps pushing and pushing and pushing, and the oil slowly works its way to this piston. And the piston, so whatever pressure you get from the pump, which I don't know, could be 100 atmospheres, you're going to get the same pressure here. So that you're going to have the same pressure. And so that's really useful, because remember that the force is equal to the pressure times the area, right? And so so you can have a little bit of area here, and where the pump is pushing the fluid into the pipe, and it doesn't take a whole lot of force because the area is small. And then over here you go to a big area, a big wide piston, so that means this area thing here is big, and you get a tremendous force. Boom, big force. And so you can now accomplish enormous things. You can tip the back part of a dump truck, which may have 10 tons of dirt in it, who knows. And that's how the hydraulic mechanisms in construction equipment work. Here in the notes, I'm saying that the force of the pump, the pump has a little piston, and the pump pushes the little piston with a certain force, and whatever that force is, it gets multiplied by the ratio of the two areas. So A2 would be the area of this piston, A1 would be the area of this piston, and it's going to be a very small piston, but it just keeps going, and it gradually, slowly, it pushes the oil through and lifts this thing up. Okay, thank you for watching.